Hello, everyone can hear me? So this is going to be a difficult talk, not for you, but for me, because in 30 minutes I have to explain to you the basics and all the weirdness about quantum computing, and then also motivate you as data scientists to take this field in a more serious way and really try to see what's going on in this area. So I wanted to make a meme, but then I was not sure if the Euro meme ban stuff is going to land me in trouble. But nevertheless, just before, I tried to make this thing. So if you have watched Ant-Man and the Wasp, there's a scene where the main guy, Ant-Man, he says, "Do you guys just put the quantum word everywhere?" Like, he was completely, like, boggled by all this quantum realm, quantum tunneling, quantum this, quantum that. And in real life, it feels like this. Every other day, you have a news article saying, oh, Google made a 72-qubit quantum processor. It's going to change everything, drug discovery, chemistry, machine learning, and so on. I mean, there are this idea, recurring idea of using quantum mechanics as something which is this all-powerful computing device or technology. But the actual science and the actual technology that we have is actually pretty limited. But then you still have all these areas where you can see some kind of quantum effects being used to develop a new technology. You have like the big government organizations like the EU Quantum Flagship Initiative to make a quantum computer. QTech, you have all the big companies, and even you have smaller companies collaborating with research institutions to build quantum devices. Of course, the news cycle creates the hype, and you have every other day articles which says, oh, big data is going to be completely changed by quantum mechanics. You have all these articles. Even at ICLR this year, this article was pretty interesting. And then you have the other side of it, which is AI controlling quantum computers, and so on. So, as I said, it's a two-way street. There are two things that can happen here. One is quantum computing and information can really revolutionize optimization, machine learning, and AI. And these are some of the references that you can look, and this is also chronological, I think, where the whole idea seems to feel like, okay, it started from here, and then someone realized you can also do this and that, and so on. But of course, all of these have some caveats, some limitations. I will speak about it. Then you have the other approach, which is adiabatic quantum computation, which is a bit of an analog approach and specifically geared towards solving optimization problems or finding the minima in energy landscape. Then there is also hardware approaches where you want to make a synapse with some kind of quantum device. For example, nanophotonic circuits, and the advantage of these kind of circuits are they're extremely energy efficient. It's a bunch of mirrors, which is your neural network, and once you shine light through it, you basically get inference with no energy costs. You also have something which is with these superconducting circuits, and people were able to show that these circuits are even faster than how the neuron computes in your brain, and of course they're energy efficient. So you have these kind of different things that's going on in this quantum AI machine learning merger. Then you have the opposite thing, where you have machine learning helping people in quantum physics. One of the most important and sort of exciting thing for me would be designing and controlling quantum experiments. So 10 years back, an experiment which fetched the Nobel Prize, which is finding a really unique state of matter, Bose-Einstein condensates. You can do it with a reinforcement learning algorithm now. You give the control of your lasers to an AI, to a reinforcement learning algorithm, and tell it, oh, I want to create this state. And it will precisely fire these lasers so that it can trap matter in a completely new phase. And this can be done in a matter of hours, where an experimentalist would take hours or days to just calibrate the instrument. So this is quite exciting. Then also, in quantum mechanics, you have problems which have an increasing amount of data. And then you can use neural networks as sort of hypothesis or ansatz to solve this kind of problems. And you have this really good paper on solving many-body problems with this neural network quantum states. And this is interesting because you need complex numbers to describe these neurons. And most of the approaches, PyTorch, TensorFlow, they have difficulty, or nobody even cares about complex numbers outside quantum mechanics. But they showed that with this ansatz, you can really solve many-body quantum physics problems very efficiently, better than the models physicists have come up with. And then finally, this is very, very recent, which is quantum-inspired algorithms. So a data scientist who works at the bridge between these two fields once realizes, oh, this weird, quirky effect of quantum mechanics, I can just mimic it in a classical algorithm, and tries to write some code. And we see that this is an 18-year-old guy, Evan Tang, from MIT, I think, yeah, he made a recommendation algorithm which is exponentially faster just by looking at what the quantum counterpart of it was doing. And he was like, oh, but this I can mimic in a classical system, hard-code it, and boom. You have an exponentially faster classical algorithm for this problem. So why are we thinking about this right now? There are several important points here, but two of them are the most important. So we have 14 nanometer chips now, which is 50 atoms apart. Apple, I think the iPad Pro has 7 nanometer chips, which would be like, and very soon, if you want to reach a limit where you have single atom apart devices, you're going to run into weird quantum effects, which will render your circuits useless. For example, the notion of a barrier in a gate in a chip is gone here, because you have something called quantum tunneling, where even though you make a wall and you want to prevent things from going from here to there, there is a probability given by a quantum tunneling effect that they'll just mysteriously appear on the other side. So all your electronics would not work at this scale. So you have to think about quantum mechanics. Of course, you have thermodynamic limits where your circuit might just burn by the heat produced just to manipulate information at that level. And then, of course, there are the other reasons that somehow quantum mechanics seems to give you an exponential advantage in tackling big data, and you can solve problems in machine learning. So bit versus qubit. We all know bits, zeros and ones. Qubits is the quantum equivalent of it, where you no longer have a 0 or 1, but you have like a superposition. But why? Why should there be a superposition of things? Why not just single 1 or 0? That's because in quantum mechanics, your reality is always described in terms of a probability wave function. I'll get to this in the next slide. Why should things have this probability wave nature? So it turns out if you do an experiment with electrons, which we know are solid lumps of, let's say, billiard balls or something, and the experiment goes like this. You have 2 holes or 2 slits where your electrons can pass through, and you keep shooting electrons through these 2 holes. You expect that because you just have 2 holes, there should be just 2 lines out there. But the electron never behaves like this. The electron gives something which is called an interference pattern, alternate light and dark bands. So scientists were like, why is this electron, which we know is a solid lump, behaving in a very weird way? And this same behavior can be completely explained if you consider a wave passing through. You would have seen 2 waves when they are at the same place at the same time, they cancel each other or raise each other's amplitudes. And so there was a crazy proposal by all the physicists starting off the last century that, okay, let's say the reality of these objects are somehow defined by the probability. And this probability behaves in a sort of wave. And so because of this crazy idea, they were able to explain this experiment and a lot of other experiments. So here is just a small animation which shows, okay, if you have 2 different possibilities and you put them together, somehow they can exist simultaneously as raising and lowering of amplitude. But then again, it's a crazy notion to have ones and zeros, or both ones and zeros simultaneously. But there's a saying called shut up and calculate. Because this is so good, this model of reality, physicists nowadays are like, okay, the math works, it gives us the result, shut up and calculate. So this is one school of thought which is like, okay, we just go with the results that it gives me. And it is one of the most successful theories that we have come across as humans, because it hasn't failed yet in any of the predictions that it made, however crazy it be. So then you would think, oh, if I can have superposition of things, it's a limitless exponential speed up over things. Like if you have 3 qubits, which can simultaneously be 1 or 0. So if you have 3 qubits, there are 8 possibilities. And now you have a superposition of all of them. So you have some sort of massive parallelization. But herein where nature kicks you in the shin, basically tells you, hey, but you can't do that because you have something which is called the measurement problem. Because the moment you look or you want to find out what is going on, nature immediately hides all the quantumness and gives you just one result. Take it, it's a 0 or a 1. You never have the notion of superposition in the results. So this is called the measurement problem. And it's a very tricky thing. If you have, let's say, a superposition of these as a quantum state, you can never basically recover these coefficients. You can never know what are these coefficients. What you do is, once you measure, you get either this or this or this, and you have to reconstruct these probabilities from the statistics. So nature just reveals you the statistics, and you have to do it again and again and again, and then you find, what the result is. Then someone might say, oh, but let's say I have a superposition, I apply a function to it, it happens parallelly, all possibilities. And then once I get the result, I make many clones of it. And I measure each of these clones, and I say, oh, 90% of the times it's this guy, so answer should be this guy. But again, nature kicks you here and says, no, you cannot do something which is cloning a quantum state. And there's a theorem for it. I wouldn't go to explain how it happens, but basically, the moment you try to find information about your system, nature just puts you in one of the possibilities instead of the superposition. So this is how quantum physicists try to write algorithms so that at the end of it, the final result that you get has a high probability of finding the answer. But you're never assured that you will get the answer 100%. So it's sort of similar to probabilistic computing. This is another very interesting experiment to show how measurement changes your reality. If you take light, which I won't say what's polarization, but let's say you have light which can oscillate in all directions. You put a filter, Polaroid filter, let's say oriented towards 0. You only let light pass which is oriented or oscillating in this direction. You put a 90-degree filter, and you know that you are not going to see any light because it's only going this way and it's going to block the path. But what's interesting is if you now put a 45-degree filter in the middle, so you have zeros, you have 90, and you have nothing passing by. But the moment you put a 45-degree filter here, suddenly you have some output in the end, which is crazy because you see that the only difference between these two experiments is putting this 45-degree filter. So somehow this 45-degree thing is recreating the oscillations in the vertical direction. How does this happen? And this happens because the moment you measure something, you sort of not only just see what the output is, but you affect it and completely change its state. And one of the ways to explain it is basically when you have this guy as 0, it is in some sense mathematically a superposition of this 45-degree guys. And then when you have a 45-degree filter, of course it can let this thing pass. And now this thing, when it's measured, it can again have two components like this. So it's some counterintuitive logic, but this works. And again, we do shut up and calculate. So, okay, another extremely weird feature is called entanglement, where two things seemingly separate on the other sides of the universe somehow share a link together. There are several incorrect notions about entanglement, and I'll try to break some of the things. But the basic idea is you take two particles, make them interact somehow, put them in two corners of the universe, and now if this person, Alice, let's say, and this person, Bob, decide to measure some property of their system, it immediately shows some correlation. So if this is a 1, this will always be a 0. Or if this is a 0, this will always be a 0. And the weird part is it's not something like you have a box and you have a red ball and a blue ball and you separate them and you know that it's going to be a red or blue. There's no magic in there. But the weirdness here comes is if they decide to measure some other property, not just up and down, but let's say left and right, they see correlations in the same thing. So it's not a matter of pre-selecting what you're going to do. It's a matter of, right at this moment, I decide to look if it's up or down, and I ask, oh, Alice, what did you see? And she sees down. And then I say, okay, let's measure left and right, and I see left, and she will see right. So somehow, the act of me looking into my quantum state is collapsing the state that Alice will get, which is a completely weird phenomena, which is called quantum entanglement. And this is actually one of the key factors why quantum computing sort of can give some advantages. But of course, this does not mean faster than light communication because of two reasons. One is you cannot use this thing as a telephone. You cannot do like, oh, now I'm going to make this down and Alice will see it up. No. The only power that you have is just looking what it is. And the moment you look it, you kill the entanglement. You collapse your system to a down, and Alice's system is a up, and you cannot do some kind of signaling with this. Then someone might say, oh, but then you still already did a signaling, because if she has a down and you have a up, you have some information exchange. But this is not faster than light, because at the beginning, both of you decide which direction you want to measure. If you don't decide that and then try to do measurement left, right, you'll only get random results. So it's kind of tricky, and nature is not so kind to us to use these awesome effects. Yeah, this is just a joke about how the Bell's theorem basically is a very nice theorem where you can show this kind of correlations in numbers. And this is just a joke that, okay, misunderstandings of Bell's theorem, or let's say quantum entanglement, happen so fast that they would violate locality, or it's faster than light. So what can we do with all that quantum? The first idea was basically to simulate quantum physics. Because if you just want to simulate how two electrons talk to each other, how a hydrogen atom behaves, as you make your system slightly complex, the amount of data that it generates is impossible for a computer to handle. It's exponential. So the first idea is, oh, if we have a toy quantum system and we want to measure some properties, we have to build a quantum computer. Then we have some very nice problems in computer science and mathematics. Factorization is one of it, where it was shown that a quantum computer can achieve some exponential advantage. Recently, you have optimization and machine learning, which comes into this picture, and people are trying to use quantum algorithms for optimization and machine learning. I'll come to that in the next slides. Then you have quantum chemistry, which is one of the most promising avenues for this, because if you want to make a drug and you don't know how it reacts to a slight change in maybe potential, energy, and you can't calculate or simulate it in a quantum, normal computer, you need to have a device which works in a quantum way. And then, of course, quantum pattern recognition, because you have these kind of quantum systems and there are some patterns. But if these patterns are a result of quantum phenomena, can you even describe it in terms of classical physics, mathematics, or with all your algorithms? So because it's a Python conference, let me give you a hands-on experience with some quantum circuits. One of the circuit is just a NOT gate. So you take a 0, it flips it to 1. But if you take a superposition of 0 and 1, now this NOT gate can flip it to a superposition of 0 and 1, and it flips the probability. So these alpha and beta are sort of the probabilities of getting a 0 or 1. Then you have something which is a Hadamard gate, which is a truly random gate. You feed it a 0, and it makes a nature-guaranteed random number generator where it will always give you a possibility of 50% 0, 50% 1. But what if now you... okay, the next thing is a 2-qubit gate, which is basically a controlled NOT. So if the first qubit says 1, only then the NOT is applied to the second. If the first qubit says 0, the NOT is not applied to the second one. And this is interesting because this is an entangling gate. This is a if-else in a normal computer. Of course, you can write this as if first qubit is 1, second qubit is 0, and so on. But this if-else is now here guaranteed to you by nature, by quantum mechanics. You don't have to write an if-else. And you can quickly see that if you parallel, I mean, if you write it for a large enough qubit state, let's say 50 or 70 bit strings, you have to do so many if-else conditions. But then if you have a quantum computer which applies this circuit, you just feed the superposition, and it gives you a superposition as a result. But again, you have the measurement problem. So you cannot expect to get the answer for every computation in one shot. You have to measure, and then you get the answer for just maybe one of the conditions. Let's say you want to solve a SAT problem, satisfiability. You enter a string and you ask, oh, does this formula satisfy this string? And if it's a 1, it satisfies and you have a solution. Now, if you make a superposition of every single possibility that you can throw at it and throw it at this computer, it evaluates, of course, parallelly because of this quantum superposition. But in the end, the result is just a 0 or 1, which says sometimes it does, sometimes it doesn't. And of course, it will be more number of times that it doesn't satisfy. If you're really lucky, in that one random shot, you will get the answer which is correct. So, of course, the measurement problem is one of the biggest problems here. So, one of the example is a quantum die. Basically, you just take 3 qubits, put 3 Hadamard gates, which randomize your qubits, and you get a sampler, basically, which gives you 0, 0, 0, 0, 0, 1 with a probability 1 over 8. So if you want to use some tool, there are a lot of Python tools to do this. This is a company called Rigetti. They have this PyQuil software. It's just writing any other Python software. You import your program, you import your qubits, you import your functions to apply on these qubits. You run your circuit, and then you do something like simulate measurement, where it probabilistically gives you one of the answers. The same thing is developed by Project Q, ETH Zurich, and it's similar. You want to take 3 qubits, you allocate it to your engine, you apply some gates to it, and you measure the qubits, and then you flush out and print what's the result of measurement. There's IBM Q, where they just let you drag and drop qubits and gates and stuff like that. So open source is playing a big role in this whole area. So these are some of the open source tools that came up, and you can see everything right now is Python, Python, Python. Like most of the interfacing is done with Python now. I would like to mention Qtip, which is more to do quantum mechanics than quantum circuits, and it's an extremely successful package, which 600 academic citations. So here now I have 8 minutes to describe something maybe which is very relevant to data science, local minima, the problem of local minima. There are quantum algorithms which try to solve this problem, and one of the algorithms is adiabatic quantum computing, or annealing. What you do is, let's say this audience is some sort of particles who are interacting with each other. Let's say this person doesn't like this person, so you wouldn't want to stay near this person. If you stay near this person, you're angry, irritated, you heat up, and your energy of the system increases. You can think of this as a system of quantum particles, where maybe these two people don't like to stay each other, or these two particles shouldn't be near, the energy of the system gets high. Maybe these two like to be near each other, and the energy of the system goes down. So what people did was they took an optimization problem and mapped it onto a system of spins, and now just by cooling down or pumping energy out of this system, you're trying to make these qubits or these spin systems get into a configuration which gives you the best possible minima. And here is like a classical simulation of this adiabatic approach, where instead of just going downhill on a gradient platform, you say, okay, I make a jump, and there's a probability that I will make that jump or not. Doesn't matter if it raises the energy or lowers this energy. This probability is temperature in physics. And you start with a large margin so that your system can run and explore everything, and slowly you anneal it, or you reduce this probability of the jump, and somehow heuristically this gives you an answer. The quantum version of it has a peculiar effect, which is this quantum tunneling, so that if you have a very high barrier and you're doing random jumps and you're not able to get out of this barrier, if this width is small, you can just tunnel through. And this is one of the really interesting phenomena, how the whole difference between simulated or classical annealing and adiabatic approach is different from the quantum approach. Then you have quantum-inspired algorithms, of course, which I talked about before. You have a M cross N matrix of recommendation, M people, N recommendations, and you want to just complete one of the rows of this matrix. If you know something, like you know some of the things a person likes, and then you would like to predict something else. Classic recommendation problem. So Ewan Tang, he started to find a proof that the quantum algorithm is exponentially a classical algorithm cannot be found which is exponentially better than the current one, and he couldn't. Instead, he ended up devising or finding a classical algorithm which is exponentially fast and matches with this Karendis and Prakash quantum algorithm. So all the quantum advantage killed in one shot. Then you have another example where people now want to preserve and say, oh, but quantum is better. We can do something with quantum that we cannot do with classical. So they design experiments or problems in quantum physics, which are called these frustrated spin problems. Similar, you put these two objects together near you, and they're frustrated because they don't want to stay near. And then you can show that by constructing these problems or defining them in a quantum mechanical way, the quantum algorithm will perform, of course, better to solve this, but the classical won't. But then here there's a very interesting thing, and this is 2018, the start of 2018, is that if someone just mimics the quantum behavior, this quantum tunneling, then both of these algorithms come to the same level. So it's not just, the quantumness which is doing it. It's the idea that, okay, this thing can happen in nature which you would never think of. Like, how would you think of penetrating, a solid wall in an energy landscape? You would not think of it. But then quantum mechanics does this, and if you hard code this in your code, somehow you can get an exponential advantage. But of course, we are just simulating this. I mean, think about this as writing a code on your computer to say, oh, instead of making a jump here, jump through the energy surface. But the quantum computer would actually do it. So in some sense, people are thinking, oh, then it's probably better to do it with a real quantum computer. Perfect. This brings me to the end of this talk. So these are exciting times ahead for both communities, because on one side you have physicists, quantum computing, quantum information researchers who are discovering this area of data science, neural networks, deep learning. And on the other side, you have quantum data scientists who are now seeing, okay, what can we do with these quantum algorithms? So I believe that maybe a bunch of quantum-aware data scientists can really help push this research forward, also in collaboration with the physicists. There are hardware challenges. We don't have a quantum RAM. We don't know that if you give me a big vector, a classical vector, maybe an image, how do I load it in my quantum system and randomly access it at each point? Because we don't know how to make a good quantum RAM. There are problems with error correction because quantum mechanics doesn't allow you to look when you are performing the experiment. The moment you look, you kill the quantumness. So how do you correct for errors if something goes wrong? So, and machine learning is playing a big role here because somehow these machine learning algorithms are sort of able to sniff out this error, correct them by themselves, and so on. Proving definitive quantum advantage. Like, there are some algorithms which are proven to be really good, really efficient, fast. But as I discussed here, there are many times where people haven't just looked carefully into the advantage. And just by looking carefully and mimicking maybe some of the behavior of quantumness, you can just destroy the advantage that you have quantum mechanically. And of course, the last and most interesting thing would be quantum pattern recognition. So if you have a quantum system, what kind of patterns can emerge? And how can you use the tools that we have now to recognize those kind of patterns? So thank you. If you want to get the slides, contact me or something. There's a website. I have a website. And I will take questions now.
Okay, so do we have any?
Thank you for interesting presentation. And one quick question. Could you briefly elaborate more on the thing you said at the end about how the machine learning algorithms can sniff into quantum computers and quantum computations?
Okay, so this error correction problem is basically, if you have a very large quantum state, you have many parameters associated with the probabilities. Is it a 1, is it a 0, or is it a 101, 100? So now, if you really want to identify this state and correct it, you would need something like, you need to know exactly all these variables and parameters and stuff. What people are trying to find out and have seen is that if you just give me some partial information about my state, maybe not the complete information, measure some of it, collapse some of it, these algorithms, neural networks or other machine learning approaches are able to somehow find some implicit way to connect this partial data to the error that would have possibly caused it, which is not completely clear to design by yourself. So somehow you just, it again becomes like a big data problem. You just give it a lot of data and somehow it sniffs out by some partial methods that, okay, this is the error that would have caused it, so I'm just going to apply this and invert this error, and so on. So I'm not completely an expert on this, but this, you could read one of the references, probably.
I got a question about the optimization. You've talked about the tunneling effect. Can you explain how is it different from, for example, if in a genetic algorithm you have random, just random change like a mutation? So
one of the things is we already have this random effect, which is stochastic jumps or some thermal effects. So this tunneling is sort of like let's say if you have if you're stuck at something here which is like very sharp and small, and if you try to do this random jumps, maybe you just keep getting stuck and getting back at it. But if you have this tunneling, then you basically tunnel through and go to the next value. So sort of different, but then again, these kind of effects, people are now just discovering both the sides. So it could as well be like a different manifestation of the same technique in classical systems.
Okay, so thank you very much again. Some applause for the speaker. Thank you very much.